Hi, my name is Sarah Billings, and this is Lab 4, Oscillations. The purpose of this lab is to analyze the motion of a spring mass system that oscillates while swinging in an arc. First, we will look at the fundamental principle, Newton's second law, and analyze a real-world video of this motion. Then, using the same physics principles, we will develop a computer model that predicts this motion. Finally, we will use the energy principle to understand how kinetic, gravitational potential, and spring potential energies contribute to the total change in energy of our system. By the end of this video, we will create a model that very closely predicts the real-world motion. The setup of this experiment is a mass 0.402 kilograms at a resting length 0.7 meters from our chosen origin. Choosing the mass as our system, we can determine the forces acting on it: the force of gravity, and the spring force. The net force is the sum of these two forces. As I just said, the best place to start analyzing this complex motion is from the fundamental principle, Newton's second law. To get the initial conditions we need to use these two equations, let's look first at our real-world video. Here you can see a setup similar to the one we just discussed, with the same mass, spring, and origin. Starting from the first motion frame, I track the spring's motion as it oscillates and swings. You can see the oscillation in both the x and y directions in these graphs. To model this same motion with the computer, we need to start from the same initial conditions and then use Newton's second law. Initial position we can get from the first data point in tracker, and since we know that the mass started at rest, initial velocity is 0. To determine F net, we need to determine the spring force. The spring constant, K, we can get from the period equation. You can find the period by subtracting the time at the lowest point of the fifth oscillation from the time at the lowest point of the first oscillation, and then dividing by 5. I calculated the period using both the X data and the Y data, and got slightly different numbers. After analyzing both, I found that the period calculated with the Y data produced a model that fit better with my real motion. This is the answer to the second "what does it mean" question. Then we rewrite the equation and plug everything in, including the period we just calculated, and we find our K constant to be 6.67 newtons per meter. To solve for the relaxed length of the spring, LO, we need to use the observation of static equilibrium, which says that at rest, the net force on the system is 0, and thus the force of gravity must equal the spring force. Plugging in and rearranging, we get LO to equal 0.1091 meters. Now we have everything we need to use Newton's second law to write a computer model. First, we input the initial conditions we just discussed and tell the program to use a small delta t between iterations. Then we input the information we need to calculate the gravitational force and the spring force. In the while loop, we define these forces, Newton's second law, and update the length of the spring. And finally, we extract our real-world data points from tracker to compare to our new computer model. Now we're ready to run our code. First, pay attention to this display window. The blue ball is our model, and the red ball is the real-world mass we tracked. Notice how they start off following almost the exact same path, indicating our model is a good simulation. The black arrow represents the force of gravity and always points down, while the blue arrow represents the spring force and always points up, indicating that the spring is always longer than its natural length. On this graph, you can see the comparison of the red real-world data and the blue model graph. In the beginning, you can see that it was a very good fit. In the end, it gets a little off. This is potentially due to forces other than spring and gravity, which we didn't take into account, that affected our real-world model. However, all in all, this is a very good prediction. Let's look at the scenario from one more fundamental principle, the energy principle. The energy principle states that the total energy is equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. We're going to assume that our system now includes the mass, the spring, and the Earth. Consequently, we can set the change in total energy of our system equal to 0. After defining the kinetic energy, the potential energy due to gravity, and the spring potential energy, we are ready to put the energy principle into our code. Here we define each type of energy, and here we define the initial energies. And finally, the change in energy, just as we discussed on the previous slide. Notice how the energy changes also oscillate. The graph of the gravitational potential energy, the green line, and the spring potential energy, the red line, oscillate with the same period that the motion changes. These changes are roughly the same size, but opposite in phase, meaning as one decreases, the other increases. The kinetic energy changes, in blue, oscillate twice as fast as the potential energy. Notice the yellow line, the change in total energy is 0 for the whole motion. This means all the other energies, the gravitational potential energy, the spring potential energy, and the kinetic energy, sum to 0, as we predicted when we first introduced the energy principle. This is the answer to the first "what does it mean" question. In conclusion, we can use Newton's second law and the energy principle to create a good prediction of the motion of a mass oscillating on a spring while it swings in an arc. This motion can even be applied to real-world scenarios like giant rope swings.